I was tasked with creating a video to display the effects of A, B, and C in standard form of a quadratic. So I decided to use Desmos to do this. It's an excellent tool for graphing, and it's going to allow me to change some values. So let's first off graph a quadratic. So we've got y equals 2x squared plus 3x. Let's go minus 2 so we can see it. So here we can see in red that it's put the quadratic down on the grid. We've got roots of -2 and positive 1/2, a y-intercept of -2, and a vertex down here at -3/4 and 3 1/8. So the question that I was asked was, okay, what do these values of 2, 3, and -2 do to the actual quadratic? And to find out, we can replace these with their letters from standard form. So the coefficient of the x squared term is often seen as the a value. So we'll add a slider for a so we can see what it does.
Pardon the interruption.
Sorry for the interruption.
Can I please have a custodian to the main office?
The second coefficient, the coefficient of the x to the power 1 term, is b. So we'll add a slider for it. And the third coefficient is c. So we'll change it to plus c, and we'll add a slider for it. So remember, our c value was -2. Our b value was positive 3. And our a value was positive 2. So that was the quadratic that we had had. Now I'm just going to go change my step here so that way it's easier to see what's happening with these values rather than having a smooth continuous step. It should slide more nicely. There. So to understand what the values of a, b, and c do, we need to start with a default quadratic. So our default quadratic is this one, y equals x squared. And of course, for y equals x squared, it's going to have an a value of 1, a b value of 0, and a c value of 0. And you can see I've now mapped my red one just directly over top of my standard quadratic. So we always compare against the standard quadratic, this y equals x squared 1. So let's take a look at what happens as a increases. So as a increases, you're going to notice the red quadratic starts stretching out vertically. So when we have a quadratic that has a term like y equals 5x squared or y equals 6x squared, we tend to see it being skinnier and being pulled inside of our standard quadratic. Now, the same thing happens as we go down. So as we get below our default value of 1 for a, we're going to notice that it's going to stretch out away from the black one. So we'll see as we get closer and closer to 0, our quadratic is getting flatter and flatter. Now, when we get to actually 0, so if we had y equals 0x squared, we wouldn't have quadratic, we'd actually have a line. So we don't tend to consider what happens when a is exactly 0 because it's no longer a quadratic. But when it's negative, something cool happens. So positive, it matched, or it was skinnier, or it was wider. And when we go negative, you may have just seen it there, it flips over. So it reflects it across the x-axis. But the same rules play. So this would be a negative quadratic. It's flipped over. It now has a maximum, but it's skinnier than the basic one. As we get toward -1, it starts to pull the shape of the black one. And you can see it's a perfect reflection across the x-axis. So it has the exact same shape, it's just reflected. And as we get a larger negative number, we see it's skinnier still. So that's the effect of the a value on a quadratic. Now let's take a look at what happens with the c value. I'm skipping the b one for good reason. So the c value, which is your last term or your constant term, it does a very simple movement for it. As c increases, you'll notice the quadratic goes up. So if c ended up being 4, the quadratic would have its y-intercept right there at 4. As c decreases, the quadratic moves down. If c ended up being 1, the quadratic would have a y-intercept right there at 1. Now I realize in this case the y-intercept is the vertex, but c controls the y-intercept. Just so happens that when b is 0, that's also the vertex. So we'll continue down, and I'll show you that as c gets negative, the y-intercept goes down. So at -2, we have a y-intercept of -2. That's all that c does. So a affects the shape, whether it's skinny and wide, and whether it's reflected. and C affects where the quadratic hits the y-axis. So we'll bring C back up to its default value of 0, and we'll leave A at its default value of 1. Now let's take a look at what happens with B. So A changed the shape, C changed the location vertically. We're probably going to think that B is going to change the location horizontally, and it kind of does. As I change B, you'll notice it does start to move slightly to the left, but it moves opposite the way we expect. As B is getting more positive, the quadratic is moving to the negative side. And it's not just moving to the left, it's moving to the left and down. And as I move back to my default value of 0, it goes back to its standard position. Now as I move to the right, as I move to the negative numbers, the quadratic is going to move to the left. And it's going to move down as well too. So B has a very interesting effect. It moves the vertex of the quadratic in a non-linear way. So it moves it kind of up and down and up and down. It actually follows another quadratic. So suppose I had B equals -4 and A equals 1. I would have the standard basic quadratic that's been moved slightly to the right and a little bit down. And now I can use my C value and change its y-intercept. So it's tough to see unless we track the y-intercept. So right now the y-intercept of the red graph is at 0, 0. If I move C to 1, the y-intercept of the red graph is at 1. So that just shows you that the y-intercept is always controlled by the C value. So what does A do? Changes the shape and the reflection. What does B do? It changes the location horizontally and vertically along some route. And what does C do? It changes the position vertically of the quadratic. So hopefully that helps you understand the parameters in standard form. Take care. Join us next time. Don't forget to hit like, subscribe, and ring that notification bell.